In this video, we're going to take a look at section 5.2, which is on systems of linear equations in three variables. All right, so in these problems, we're going to have three variables to contend with, and generally those variables will be x, y, and z. When we type our answers into Math Excel, you will type the answers in alphabetical order, forming, instead of an ordered pair, you form an ordered triple. So our answer will have the form of x, comma, y, comma, z. And we'll put parentheses around that. When you have three variables, in order to get a specific solution out of the problem, you have to have three equations. Kind of said that backwards, but whenever there's three variables, you need three equations to get a specific solution. Not all system of equations produce a solution. Sometimes you might have one that has no solution, and there are some that can have infinitely many solutions, so we have to be on the lookout for those as well. Generally, when I'm teaching, I like to give step-by-step directions on how to do the problems and, type those out. I could do the same thing with this type of problem, but I find that just showing the process seems to work better than describing it verbally. So I'm just going to walk us through the steps of solving this. The difficulty with three variables is that when you are reducing the equation down, the best you can normally do is to get rid of one variable at a time. So if you go back to the video for section 5.1 with two variables, you can get rid of one of them and you're left with just one, right? Because you only have two to start with. You eliminate one of them, you only have one variable left, so you can find the solution for that variable. But with three variables, we can get rid of one, but then we still have two variables left to deal with, so we don't actually get an answer right away. And so we're going to have to jump through some hoops to whittle it down to two variables first, and then once we have two variables, we can whittle it down to one variable. In order to do that, though, we have to have two equations with two variables, right? So if we can eliminate one variable, we can get it down to two variables, but then we need two equations with those two variables before we can go any further with that. And so here is the generic process for getting through this type of problem algebraically. There are exceptions to these steps that I'm about to give you, depending on the problems that you're dealing with. But in general, this is the way you want to try to approach these problems. So step one is we want to use two of these equations to eliminate a variable. And then we'll have two variables left over. And this first step is completely open-ended. You can use any two equations to eliminate any variable that you want. So make it easy on yourself. Pick the easiest two equations, eliminate the easiest variable that you can eliminate. So we're going to use equation blank and equation blank to eliminate blank. All right, so we have to make some choices here. Keep in mind the purpose of step one is to have an equation with only two variables. That is what you want out of step one. There will be some problems later where that's already done for you, where you already have an equation that only has two variables. Then you don't have to do step one because it's already given to you. But here, all of these equations all have three variables. So we're going to use step one to create an equation with just two variables instead. All right, so it's our choice. Usually I would ask my class, which variable do you want to eliminate? And I would just kind of go with whatever choice they make. I'm looking at, let's see, any of the three could work fairly well. Let's just go with y. I'll eliminate y. It seems like an easy one to eliminate. So I can use equation 1 and equation 2. So they're numbered over here. And I chose to eliminate y. There's other things you could do here. To eliminate y with these first two equations, I need to have a 2 here, right? Because if I have negative 2y plus 2y, those would cancel each other out. So to get a 2 here on this first equation, I'm going to have to multiply both sides of the equation by 2. All right, so this is the first equation. We'll multiply both sides of this equation by 2. Make sure you do that to both sides of the equation. One of the most common mistakes I will see on these problems is students making the right choice, but forgetting to multiply it to both sides of the equation. So make sure you multiply it to both sides of the equation. So I'll multiply 2 to both sides and make sure you distribute here. So we're going to get 10x minus 2y plus 2z equals 16, right? So that's equation 1 modified, so that the y variable will cancel out. And then equation 2, we don't need to modify, so I'm just going to copy it down. I'll do a different color here. So we'll have 3x plus 2y minus 3z equals negative 18. So I just copy down equation 2. Now I will add both of these equations together. And what's going to happen is we'll get 13x when we combine the x's together. The y's are going to cancel each other out. And then we're going to get negative z here, right? So 2z minus 3z gives me negative z equals, adding the right-hand sides together, I get negative 2. So this is the outcome of step 1. We use 2 equations to eliminate one of the variables. And the result is now I have an equation with just 2 variables, x and z. However, in order to get a solution for x and z, I have to have 2 equations with those 2 variables instead of just 1. So that leads me to step number 2, which is to use a different pair of equations. So I can't use the 1-2 combo again to eliminate the same variable, right? Because I want to have a second equation with x and z. So I need y to be eliminated again. So we're going to use a different pair of equations. Use a different pair of equations. And so we'll use blank and blank. We'll have to make a choice again to eliminate, let's try that again, to eliminate y. I don't have a choice on that. If you eliminate y in step 1, you have to eliminate y in step 2. So our options are much more limited in step 2. We can't use the 1-2 combo, which means we only have 2 choices. I can use equation 1 and equation 3, or I can use equation 2 and equation 3. Those are the only 2 pairings that are left. And I don't have a choice on which variable I want to eliminate. I have to eliminate the y variable. And so I will choose equation 1 again, because this one's just really, it's a nice base to start with to eliminate other, terms. So, because there's a 1 in front of it. So I can make any number I want here by multiplying that number to both sides of the equation. So I'm going to use equation 1. And so I can't use equation 2 again because that's the 1-2 combo. So then that forces me to choose 3 as my second equation. And what I'm going to do is the same thing I did here. I'll start with the first equation, 5x minus y plus z equals 8. I want it to cancel out with the negative 3y here, which means I need to have a plus 3y in the first equation for those to cancel each other out. To make this a positive 3y, I will have to multiply both sides of the equation by negative 3. So I'll multiply the left-hand side by negative 3, multiply the right-hand side by negative 3. And so here I'm going to get negative 15x plus 3y minus 3z. Let's see, I don't know. I don't think it's going to let me write. I don't want to do that. Okay, I've done this before, but I feel like I've forgotten how. Okay, I guess maybe if I just do this, I got more space. Okay. All right, and where was I at? Okay, equals negative 24. All right, so, okay. So that is the first equation again, modified so that it will work out with the third equation. But the third equation, we are just going to copy down up here, and we don't have to make any modifications to it. It's ready to go. So we're going to copy that down. X minus 3y plus 2z equals 22. All right, so that's equation number 3. We didn't have to make any changes to it. And now I will add these 2 equations together, just like we did over here. We'll get negative 14x. The y's cancel out again. Negative 3z plus 2z is again negative z, equals, when I add the right-hand sides together, I get negative 2. Right, so the result from step 2 has to be another equation with the same two variables that you had from step 1. So we have x and z here, we have x and z over here, so this is where you want to be after step 2. Step 3, let me make a little more room here. Step 3 is to solve these two equations as a system of equations. So I have 13x minus z equals negative 2 from step 1. I have negative 14x minus z equals negative 2 from step 2. So solve this as a system of equations of two variables, like we learned to do in section 5.1. So I will use elimination method here. I'm going to choose to eliminate the z variable. They're almost ready to cancel out, except they're both negative. I need one of them to be positive. So I will make the bottom one positive by multiplying both sides of the equation by negative 1. Right, and so what we're going to end up with here is the top equation will stay the same. We have 13x minus z equals negative 2. The bottom equation becomes positive 14x plus z equals positive 2. And we're going to get kind of a unusual answer. There's nothing wrong with it, but it's not very common, I would say. We'll add these two together, the z's cancel out, and now I'm down to just x. And now I can get a solution, right? This is going to give me 27x equals, the right-hand side, when I add those together, I get 0. And so we get 27x is equal to 0. Solving that for x, we divide 27 on both sides. It's a crazy number to get. And I remember doing this problem in class the first couple of times and feeling a little bit worried about the way these numbers are looking. But it doesn't really matter what number you get here in front of x if the right-hand side is 0, because then that number just goes away, right? 0 divided by 27 is still just 0. Right. And so we get x is equal to 0, which, like I said, is a little unusual, but not a problem at all. It's just like any other number. So we get x is equal to 0. Now, sometimes students get excited about having a number for one of their variables, which it's good to be excited about. You're getting through the problem. But what you can't do is, or what you don't want to do, I guess you can do this, but I think this would be the more difficult route to take, is a lot of students, thinking back to 5.1, they're like, okay, I got a number, plug it back into one of my original equations. So they go all the way back to the beginning and they plug in 0 for x up here. And you can make that work, but like I said, it's going to be more work than doing what I'm about to tell you, which is don't leave step 3 early. Don't exit step 3 too soon. Make sure you squeeze all the information out of step 3 that you can. We found the value for x. We can also get z while we're here, right? We have two variables. Once we find the value for one, we can get the other one right away by plugging it back in here, right? In one of these two equations. So not one of the very original equations, but one of these two here that are in step 3. And so I think I'll choose the top one because it just, I don't know, it looks a little more friendly to me with this negative sign here. I think this one looks a little more friendly. So we're going to plug it in here. We'll have 13 times 0, right? I'm plugging in 0 for x. I guess it doesn't really matter what that number is, right? Because if we're plugging in 0, that term's just going to go away. So it really didn't matter. I gave it more thought than I really needed to. We get 13 times 0, which is going to be 0. Whoops, that's not a z, that's a 2. And so the 0 just goes away. So we get negative z is equal to negative 2. Solve that for z by dividing negative 1 on both sides. And you see how quickly we arrive at our second conclusion, right? It would have taken you much more time if you had plugged 0 back into one of the very original equations. And so now we have two numbers. So now we're ready for the last step of the problem, which is what you might have been tempted to do earlier. Now that you have both of these results, plug both of them back into one of the original equations, and you will get your final result, right? Because with 3 variables, we need 3 numbers. We need 3 numbers to be a solution. And so going back to the original equations, by far, I don't know, I thought there was an easier one here. I was going to say by far the easiest one would be the first one, but now that I'm looking at it again, maybe not the case. These are all kind of the same difficulty level. But you want to look for the easiest equation to use. There isn't really an easiest one here, so I'll just use the first equation. The numbers are a little bit smaller at least. So we have 5z minus y plus z equals 8. So let me see if I can remember that. I'll just plug those two numbers I found into this first equation here. So 5x, I might have said the wrong thing earlier, but 5x, I wrote this one down enough, I should remember it, 5x minus y, I already forgot, 5x minus y plus z equals 8. Okay, plus z equals 8. And we will plug these two numbers into this equation to get our last result. It really does not matter which equation you use in theory, because you'll get the same answer regardless. So while I'm deciding which equation to use, I'm trying to do that because I'm being lazy and I want to make this as easy as I can on myself, but not because it makes a difference in the answer. The answer will be the same whichever equation I pick. All right, so let me see if I have enough room left on this page. Okay, I guess it just keeps scrolling down forever if I need it to. So I'm going to plug in 0 for x. I'm going to plug in 2 for z. And with those two numbers plugged in, I can now solve for y. So just like we saw happen up here, when I plug in 0 for x, I'll get 5 times 0, which is 0. And then that's just going to go away. So I'm just going to drop that. And then I'm going to focus on this, solving it for y. I will subtract the 2 to the other side. I get negative y is equal to 6. And then I'll divide by the negative sign on both sides, which is like a negative 1. And I get y is equal to negative 6. Let's try that one more time. All right. And so we get a value for y. So now we are done. So once you get a value for x, a value for y, and a value for z, you've solved the system of equations. So our final answer, as I mentioned at the beginning of the video, is you want to write it as an order triple. So this will be 0, negative 6, 2. And that's how you will type it in. All right, let's take a look at another example. Here, you might notice, and this might seem contradictory to what I said earlier, we have three variables, right? X, Y, and Z, but there's only two equations. And I mentioned in the previous example that with three variables, you need three equations. But I also had more to the sentence than just that. If with three variables, you need three equations in order to have a solution, a specific solution to that system of equations. So we will not get a specific solution here. What's going to happen is we will get infinitely many solutions because there's not enough equations to help us narrow it down to a specific answer. We'll end up with an infinite number of solutions instead. So we are going to try to manage this in the same way we did the previous example. Obviously, it's not going to work exactly the same with only two equations. But the first step we can still do the same way. Use two equations to eliminate a variable. We can at least do that, right? We have two equations here. And in fact, one of the variables is already set up to be eliminated. So I could think of it like this. I'm just going to go ahead and make sure y gets eliminated. And I don't have to make any changes for that to happen. So I'm just going to take these two equations and add them together the way they are. And I know a variable will get eliminated. All right, and you might already notice that something else is going to happen for us as well. All right, so let's go ahead and add these equations together. You get negative 2x minus 4x. That'll be negative 6x. The y's cancel out, as we were prepared for. But maybe what we didn't prepare for, because we weren't really looking at it, is that the z's also cancel out. So that's a bonus, right? Anytime you're dealing with three variables, if you can find a way to eliminate two variables at the same time, that is a shortcut that you should take. So be on the lookout for that. If you find a way to eliminate two variables at once, you should go ahead and do that. It's going to get you to the answer that much quicker. So that just kind of automatically happens here. On the right-hand side, we get negative 2 minus 4, which will be negative 6. And with these two variables gone, this is all we have. Negative 6x equals negative 6. And because two variables were eliminated, I can go ahead and solve for the remaining variable. So I'll divide -6 on both sides, and I get x is equal to 1. And so I mentioned there's going to be an infinite number of solutions to this system of equations, but whatever those solutions are, the x coordinate will always have to equal 1. So it's a really interesting solution set. So the y and the z coordinates will vary, and they'll all equal lots of different things. There's an infinite number of possibilities there, but x is always equal to 1 every single time. There's no wiggle room with that. So now that I know x is equal to 1, I can plug this back into one of my original equations, because I really can't do step 2, right? Step 2 would be use a different pair of equations to eliminate the same variable. Well, there isn't a different pair. And so it kind of messes up our process. So we have to be flexible. We adjust to that. We happen to eliminate two variables at once, so that we should take advantage of that. But also, we can't do step 2 and step 3 because we don't have enough equations to do that with. So this was the best that we could get. So let's just skip to step 4, which is to take our result, plug it back in to one of the original equations. So I'll go ahead and plug it back in here. And so we're going to get -2 times 1 minus y plus 2z is equal to -2. And let's just find out what we can learn about this. Now that we know x is equal to 1, what is that going to tell me about y and z? By plugging it back into this equation, we're going to get some information about that. All right, so this is going to give me -2 minus y plus 2z equals -2. I can add the 2 over to the other side, and the 2's cancel out. We get -y plus 2z. Here the 2's cancel out, and we'll just have 0. So what I can do with this equation is I can solve it for one of the variables, and it'll give me a relationship between the y-coordinate and the z-coordinate. The easier variable to solve for would be y, and the easy way to do that, instead of subtracting the 2z over here, is to add the y over here instead and get y on the right-hand side. And so we're going to get 2z is equal to y, and that's solving it for y. I could flip it around the other way, y is equal to 2z, right, if that's better. All right, so what I've just learned is that there's going to be an infinite number of solutions, but whatever those solutions are, the y-coordinate always has to be 2 times the z-coordinate. So for example, one possible solution, so remember the solutions are x, y, z. X is always equal to 1, so that always has to be a 1. I could pick the z-coordinate to be any number I want. Here's where the infinity gets introduced to the situation, right? I can pick z to be any number. So let's pick z to equal 3, for example, just off the top of my head, just making up a number. However, if I make up a number for the z-coordinate, the y-coordinate has to follow this rule. So I do not have a choice in what the y-coordinate is. I can't say, let's have the y-coordinate be 10. I'm not allowed to just arbitrarily pick a number for the y-coordinate. We have a formula that we have to follow for the y-coordinate. So z can be anything you want, but then the y-coordinate has to be 2 times that z-coordinate. So if I pick 3 for z, the y-coordinate would have to be 2 times 3, which is going to be 6. Sorry, that really came out weird. I don't know why I wrote it like that. Okay, let's try it again. All right, has to be 6. And so we'd have to put a 6 here for the y-coordinate. This is one solution to the system of equations. You can test it out if you want. Take these numbers, plug them in for x, y, and z. You'll see that it comes out true for both equations. That's what makes it a solution. It has to work in both of the equations that were given to us. However, we can generate another solution. If I pick a different number for z, I'll get a different solution. So again, x always has to be a 1, but let's pick z equal to 4, right? Then what would the y-coordinate have to be? The y-coordinate would have to be 8, right? The y-coordinate has to be twice whatever the z-coordinate is. So this is another solution to the system of equations. And we could generate another one, right? I could pick, not 8, why did I put 8? I could pick 5 for z, and then the y-coordinate would have to be 10. I could pick -2 for z, in which case the y-coordinate would have to be -4, and that's another solution. So I can generate an infinite number of solutions this way by just picking different z-coordinates and then computing the y-coordinate that has to go along with that. And then the x-coordinate's always equal to 1 for this particular scenario. All right, So how do I type this into Math Excel? So the way you're going to type it in is Math Excel will have like options. It'll have like option A, the solution is blank, comma, blank, comma, blank, right? You would pick option A if there's one solution to the system of equations, which is not the case here. So you don't want to pick option A. Option C is like no solution at all, which is not the case here. We have an infinite number of solutions. So you should see an option, I think it's usually the second one, that's going to be set up like this. Blank, comma, blank, comma, blank. And it might be set up like this, I'm trying to remember, such that, let's see, it'll be like, such that z is any real number or something like that. And I'm really making a mess here. I probably should have wrote this, in a different space. But you want to pick this option that has like this set notation and where a variable is fixed. And I think they'll usually anticipate which variable you're going to end up solving it for, because most people wouldn't look at this scenario and solve it for z. They're going to assume you would solve it for y. So I think they're going to have z already populated here, and it wants you to fill in the other two spots. So we know x always has to equal 1, so we'll put that there. And then for the y coordinate, you put this formula. So the y coordinate has to always be 2 times whatever the z coordinate is. And this gives you like a blueprint for generating solutions to the system of equations. So this is how you'd want to write your answer for this system. That z can be any number you want. The y coordinate has to be 2 times that z coordinate, and then the x coordinate's always equal to 1. And so that would be our system of equations, or our solution to this system of equations. All right, and this is called a dependent system. So remember, if you watched my video for section 5.1, the dependent systems, when there's only 2 variables, is a really silly situation. You have the same equation twice. So I really don't like that problem because it's a silly system of equations that doesn't really make sense. But the dependent systems in 5.2 are much more interesting, as you can see. All right. So let's take a look at this system of equations. So this one I don't think is going to be dependent, but what is unusual about this one is that while there are 3 variables in total, no one equation has all 3 of the variables. So they're kind of missing from the various equations. So again, we have to adjust our steps given that situation, right? So remember, step 1, we want to use 2 equations to eliminate 1 variable. Well, we don't need to do any work. Let's back up there. So that was the prescription, which is use 2 equations to eliminate 1 variable. But what was that prescription for? It was to end up with an equation of just 2 variables. That is the whole goal of step 1, is to have an equation with only 2 variables in it. And normally, in most ordinary circumstances, you have to do some work to make that happen. But for this particular problem, you don't, because it already has equations with only 2 variables. So don't just memorize the steps, understand why the steps are being executed, and that will help you find shortcuts like this, or help you adjust when the equations aren't normal or behaving the way they normally do. So for step 1, all I want for step 1 is an equation with 2 variables. This time I don't have to do work to make that happen. I can just pick one of these equations they've given me. I'll just use equation blank as my result for step 1. All right, so I have equation A, I have equation B. Let's rewrite the A there, it looks kind of funny. I was going to put 1, but I changed my mind. So we have equation A, equation B, equation C. I'm going to use equation A as my result for step 1. So my conclusion for step 1 is just x plus y is equal to 13. It was given to me. I didn't have to work for it. I have an equation with 2 variables, and that's what I'll use for step 1. All right, so that's how we adjust in this situation. Now for step 2, remember the goal of step 2 is to have a second equation with the same 2 variables as step 1, right? So in step 1, based on my choice here, I chose the equation where I have x and y as my 2 variables. So for step 2, I have to have another equation with just x, and y. I don't want z to be around for step 2. Unfortunately, they didn't give me a second equation with just x and y, so this time I'm going to have to work for it. I need to use 2 of these equations to eliminate z. I don't know why I left the d out here for and. To eliminate z so that I end up with an equation of just x and y. So which 2 equations do I have to use? I don't have a choice here. There's only one choice you can make to have z eliminated so that you have an equation with just x and y, and that's b and c. So we'll have to use b and c to eliminate z so that I end up with an equation with just x and y as my variables, right? And so we have y minus z equals 5 as my first equation. We have, and so be careful here because there's only 2 variables. They were kind of sloppy in the way they align these equations. The x and the y really should not be on top of one another because they're not like terms. So what I would recommend is making columns for each variable. So this is the y variables column. And so I'm not going to put x underneath it because this is really for the y variable. The x variable should have its own column. And so I'll move it over to the side. So this is the column for x. There is no y variable in the second equation. So I'm going to skip over this space. I'm going to try to skip over it. And then I'll put plus z in the z column because, it's the z variable. So it belongs in the same column with this one. Equals 8. All right, so that's the way I would organize those 2 equations. So I'm using the bottom 2 equations, and I'm going to eliminate z so that z is out of the picture. That way, I only have x and y remaining. Right? Okay. And what's really nice about this choice that I made to just use x and y for step 1 is that eliminating z here is about the easiest thing we could have done. Right? It's already set up to be eliminated. All I have to do is add these 2 equations together. There's nothing to combine the x with, so I'll just copy it down. There's nothing to combine the y with, so I'll copy it down. It's a positive y, so I'll need to put a plus sign in front of it. The z's get eliminated, and on the right-hand side, I get 5 plus 8, which is going to be 13. And so for step 2, I end up with a second equation that has x and y. Right? A second equation with the same 2 variables as I had from step 1. So this one has x and y, this one also has x and y. From here, the rest of the steps work as usual. So once we had to make some adjustments to our steps because of the unusual nature of this problem. But once you get steps 1 and 2 done, you're back in familiar territory, hopefully. All right, so for step 3, I want to take my results from step 1 and 2 and solve it as a system of equations of just 2 variables, right? So I have x plus y. Okay, I was like, oh, this won't have an infinite number of solutions. I'm wrong about that. You probably saw this already. I just now noticed it. The equations are the same. So what's going to happen here when I try to solve this system of equations with these 2 variables here? I need to eliminate one of these variables. Let's say we choose to eliminate y. I need to make one of these negative. So I'll make the bottom one negative by multiplying by -1. So I get x plus y is equal to 13. I'm just copying the first equation over. The second equation, I get negative x minus y equals negative 13 when I multiply it through by a -1. And now I will add these 2 equations together and everything cancels out. Right? The x's cancel out, the y's cancel out, the 13's cancel out. So what happens if everything's eliminated from one side of your equation? It means you have a 0. And same thing over here. 13's are eliminated, means we have a 0 left here, so we get 0 equals 0. We talked about this in the previous section in 5.1. This is, if you're trying to solve your system of equations and all your variables disappear on you in that process, you have a special case. And it either means you have infinitely many solutions or you have no solution at all. And the way you tell the difference between those 2 outcomes is whether this is positive or negative, right? And so we see that this is not positive or negative. It's so weird how brains work. I meant to see whether this is true or false. Isn't it weird how, I don't know, I think most people's brains associate true with positive and false with negative. I don't know. So I'm sorry I misspoke like that. That was really weird. So the way you tell the difference between infinitely many solutions and no solution is whether this comes out true or false, is what I meant to say. And this one's true, right? Which means we have infinitely many solutions. So it's actually a case like the last problem, infinite solutions, which also means it's dependent. I don't know if it's going to ask you about that classification, but that is how we would classify it. So it's infinitely many solutions. So that means we want to choose the option. So there's no further for us to go. So I mentioned, it's the same as the first problem, but once your variables just completely disappear, you don't need to go to step 4, right? You're done. You have your conclusion. We have an infinite number of solutions here. We just jump to the answer. So our answer here, we're going to pick for infinitely many solutions, the thing I mentioned last time, the one that looks like this. Such that, and it's going to be like, set up like this, such that blank is any real number. I think it should look something like this in your options. Now, what I'm not sure about is which variable they will have prescribed here. So they should have a variable automatically filled in. I'm not sure which one they're going to actually choose for you there. I'll tell you how to adjust in case it didn't work out. In case the variable they've selected for you doesn't really work with the way you did the problem. So here, the way we chose to do the problem, I guess it doesn't really matter in this problem now that I think about it, because all the equations only have 2 variables. So you should be able to figure it out. Whichever variable they pick here, just kind of go back to one of these original equations and choose the equations that have that variable. So, but it is possible to switch from one variable to another. So let me go ahead and make that point still. So let's say I base it off of my choices here. So I have x and y. Let's go ahead and solve this equation for y. If I solve it for y, I will subtract x to the other side, and I get y is equal to 13 minus x. So what that tells me, again, we have an infinite number of solutions, but it doesn't mean anything works. 0, 0, 0 would not be a solution to this system of equations. So there's still things that don't work, even though there's an infinite number of things that do work. So we have to be careful in how we describe the solution set. What this equation is telling me is that whatever the infinite number of solutions are, what has to be true about those solutions is that the y-coordinate must always be 13 minus the x-coordinate. So I can pick anything I want for x, but then the y-coordinate has to follow this formula. It has to be 13 minus whatever's chosen for x. So for example, I could choose, so remember our solutions look like this. I could choose x equals 4, but then the y-coordinate would have to be 13 minus 4, which means the y-coordinate has to be 9. So x can be any number I want. There's where the infinity gets introduced, right? I have an infinite number of choices for what I choose as my x-coordinate, but then I do not get to choose the y-coordinate. The y-coordinate has to follow this formula. So if I choose x equals 4, the equations tell me then the y-coordinate has to be 9. You don't get to pick that one. The y-coordinate has to be 9. And same thing for z. I will not get to choose the z-coordinate. It will have to be computed based on my choice for x. So by solving this equation for y, what I've chosen is for the x-coordinate to be any number I want. So that's going to be the variable that's automatically filled in for me. So x can be any real number. But then the y-coordinate has to be determined by this formula. It has to be 13 minus x. So whatever I choose for x, the y-coordinate will be 13 minus that number. What about z? So the z-coordinate will have to also be based on my choice for x. And to find out how it depends upon x, you have to go back to your original equations. And the bottom equation here relates the x-coordinate to the z-coordinate. And so I want to use this bottom equation and solve it for z, so I can know what z has to equal based on x. Right? And so I'm going to take this equation, x plus z equals 8, solve it for z by subtracting x to the other side. And I get that the z-coordinate has to be 8 minus the x-coordinate. So I can pick whatever I want for x, but then the z-coordinate has to be 8 minus whatever I choose for x. All right. So let's go ahead and fill that in down here. So we're going to have 8 minus x as our z coordinate. So on Math Excel, if they already have x as the variable that's automatically filled in, this will just be on the screen already, but you will have a box for typing in the y and the z coordinate formulas. And so you'll type these into those boxes. The rest of it should already be typed out on your screen. However, let's say that it's not x that is pre-filled in on Math Excel. Let's say they've pre-filled in z, like our last problem that we had, where z is any number. All right, so let's say Math Excel has it set up like this. Now you, through your work, ended up getting the solution in terms of x. And also, I guess, well, let me finish this thought out real quick. I'm sorry, I forgot to do this. So given this example, right, this is just one of infinitely many possible solutions. I picked 4 for x. I just made that number up and picked it, plugged it in for x, and I got y has to be equal to 9. What would z have to be equal to in this case? Z would have to be 8 minus that choice for x. So z would have to be 8 minus 4, which is also happens to be 4. So this is one possible solution of infinitely many solutions that are possible. I'm sorry, I said the word possible there twice really quickly, back to back. Now, I wanted to finish that thought so that I could make a point with what we're about to do here. So the way I did the first result here is I wrote the solutions in terms of x. So my blueprint for my solutions is in terms of the x variable. However, we can switch it to be in terms of whatever variable we want. So I can rewrite the blueprint for my solution set in terms of z instead of x. And the way you would do that, to switch it, and so you don't have to start over and like do the whole problem over again and solve everything for the other variables in terms of z, you can just use the solution you already have and convert it to the z variable. So we already have it in terms of x, we can convert it to z. The way you would do that is you take the z coordinate here, which is z equals 8 minus x, and then you solve that for x. So rearrange this and solve it for the other variable. Right, so I'll add x back to the other. No, I don't want to add x. Do I? I don't know. What's the best way to do this? Yeah, let's add x back to the other side. So I get x plus z is equal to 8. And then I will subtract z to the other side. And I get that x has to equal 8 minus z. Now I have the x coordinate in terms of the z coordinate. So this allows me to choose whatever I want for z and then have a formula for calculating the x coordinate in that case. Right, so you always get to pick one of the coordinates, but then the other two coordinates have to be calculated from a formula. Right, and so x would have to be 8 minus z in this case. Right, so this is how you would adjust. If you got your solutions in terms of x, but Math Excel wants the solutions in terms of z, this is how you would adjust to that. Now we still need the y coordinate here, and the way you would get that is to take your result from x, plug it in to the y coordinate of your original result, and it will change it from being in terms of x to being in terms of z. So I'm going to do a substitution. I'm going to replace the x variable here with 8 minus z. So that takes the x out of the y coordinate and puts z in its place, right? So I'm going to get 13 minus, be careful with the minus sign, 8 minus z. And then we distribute the negative sign to both of those. So we get 13 minus 8 plus z, which is going to give me 5 plus z as my y coordinate. And that's the y coordinate in terms of the z variable now. So I took x out of it, put z in its place. And so now the y coordinate can be computed in terms of my choice for z. So this would be another way of writing the same solution set. I forgot the curly brace on the other end here. And you might say, wait a minute, this is the same answer? This is the same solution set. Even though it looks completely different, this formula, this set of formulas will generate the same exact solutions as this set of formulas will. And I know it's surprising, it doesn't look like it would, but it does. So to make my point, unfortunately, I got, z and x being the same up here kind of makes it a little bit harder to accept, I guess. But I can generate the same solution set from both of these, right? So here, z is equal to 4. So let's make that choice here. I'll let z equal 4. It's my choice. I'll let z equal 4 here. Based on that choice, what would the y-coordinate have to be? It'd have to be 5 plus 4, which will be 9. And then the x-coordinate would have to be 8 minus 4, which again would be 4. And I get the same exact answer that I had up here, right? So it will generate the same exact solution set. The only difference is this, the first one I did is in terms of the x variable, so I get to choose the x-coordinate, and then the y and z-coordinate are computed. Here, I get to choose the z-coordinate, and the x and y coordinate are computed, but it generates the same set of solutions either way. All right, let's do another one just to really drive the point home. So let's pick a different number for x. I'll pick 1 here. So if I pick 1 for x, then the x-coordinate would be 1. The y-coordinate would be 13 minus 1, which will be 12. The z-coordinate would be 8 minus 1, which is going to be 7. Right? That's another solution to this system of equations. Will this one generate the same solution? Yes, it will. If we pick z to be 7, so we want to match that z-coordinate there, so I'm going to pick 7 for z. If I plug in 7 here for z, I get 5 plus 7, which is 12. And I'll get 8 minus 7 here, which is 1. And it gives me the same solution. So it will generate the same solution set either way. All right. So that's a dependent system. So they're very interesting. They take a lot of time to talk about the intricacies of it. But in terms of the amount of homework and the amount of test questions that you should have on dependent systems of 3 variables, you shouldn't have to encounter it too often. So I'm sorry I spent a long time explaining it, and it probably will be just maybe 2 questions on your homework. And it's the same 2 that we saw here on the video today. All right, so I have 2 more examples here, and I know I'm already at 45 minutes for this video. These are word problems. I'll try to do them as quickly as I can to keep the video under an hour, hopefully. And this is really one of my favorite problems in the course. I think this is so interesting. We're talking about a quadratic function here. Now, we did quadratic functions back in chapter 3. We know that a quadratic function is a parabola. So if you were to graph a quadratic function, the graph is a parabola. For a line, how many points do you need to graph a line? You need 2 points, right? Give me 2 points, and you can determine the graph of the line, and you can determine the equation for that line. What's really fascinating to me, because it just doesn't seem like it should be possible, but for a parabola, how many points do you need to have a particular parabola? You only need 3 points. So any 3 points determines one particular parabola that can pass through those 3 points. So if I just give you 3, random points here, there's only one parabola that can possibly pass through those 3 points, which doesn't seem possible, right? Because my imagination, I can think of lots of like U shapes that I could somehow pass through those 3 points. But it turns out that there's only one parabola that can possibly pass through 3 given points. Just like there's only one line that can possibly pass through 2 points. And this exercise really proves that. All right, and so this problem's a little hard to follow. So what we're going to do is they're giving us 3 points. We want to plug those points into the formula for a quadratic function. So we're going to be plugging these points in for x and y. Okay. So we have 3 different points to plug in for x and y. And then what we're going to do to figure out the equation of the parabola that passes through these 3 points is we have to figure out the values for a, b, and c. So the thing that's kind of getting flipped around on us here is that for our system of equations, the variables are a, b, and c. So it's 3 variables. We'll have to have 3 equations, which is why you need 3 points, which is why this concept works. Because to determine a quadratic function, you have to have these 3 numbers, a, b, and c. And that's 3 unknowns, so you need 3 points to have 3 equations to solve for those 3 unknowns. That's why 3 points gives you that unique parabola. All right, anyways, we'll plug in 1 and 6 for x and y. So I'll plug in 6 for y, right? So this is the point 1, 6 getting plugged in. We get 6 equals a times 1 squared plus b times 1 plus c. So that's going to give me 6 equals 1 squared is 1. 1 times a is just going to be a. B times 1 is b, and then the c gets copied down. So this is my first equation. The second equation, we're going to get negative 1 comma negative 4. We're going to plug that in. So negative 4 gets plugged in for y. We'll have a times negative 1 squared plus b times negative 1 plus c. So we're plugging in negative 1 for x. Negative 1 squared is again positive 1. So we're going to have negative 4 equals a times 1, which is a, b times negative 1, which is negative b, and then the c gets copied down. So that's my second equation. My third equation we'll be plugging in 3 comma 10. So we plug in 10 for y. We'll have a times negative 3 squared plus b times negative 3 plus c. That's going to give me 10 equals negative 3 squared is 9, so 9 times a, which is going to be 9a. B times negative 3 will be negative 3b. The c gets copied down. And so that's my third equation. All right, so let's go ahead and write them over here. So we have 6 equals a plus b plus c. We have negative 4 equals a minus b plus c. And we have 10 equals 9a minus 3b plus c. And we want to solve this system of equations. So we'll go through that same generic process that we did for the very first example, and it should work pretty nicely here because this is a more ordinary, typical kind of system of equations. And so I have to use 2 equations to eliminate 1 variable. C is a really good choice here because it's just C in every single case. But I'm really leaning towards B because B is going to be really easy to eliminate in the first step. And then for the second step, I think it'll be pretty easy to do as well. So I'm going to go for eliminating B. But if you chose C or even A, any of those work out just fine. So the first step, I choose 2 equations. So let's say this is equation A, and this is equation B, and this is equation C. I'm going to use A and B. Maybe I shouldn't be calling them A and B here, to eliminate the variable b, lowercase b. Right. And it's already set up to eliminate, so I don't have to do any setup work here. I just add the 2 equations together. So here's A and here's B, equation A and equation B. I'll just go ahead and add the 2 together the way they are. So 6 plus negative 4 is going to give me 2. A plus A gives me 2A. The b's cancel out. C plus C gives me 2C. All right, so that's my result from step 1. I end up with an equation of 2 variables, A and C. So for step 2, I want the same thing. I want another equation with the variables A and C so that I can solve that as a system of equations of 2 variables. All right, so let's go to step 2. Let's make some room for that. So that was step 1. Step 2, I have to use a different pair of equations. So use blank and blank to eliminate B again. So I don't have a choice on that. If I chose to eliminate B in step 1, I have to eliminate B in step 2. And I have to use a different combo. I can't use the A-B combo again. So I will use equation A with equation C. Right? And I will have to eliminate B. So we have 6 equals A plus B plus C. That's my first equation, equation A. Equation C is 10 equals 9A minus 3B plus C. I have to eliminate B. And so in order to do that, I want a 3 to be here in front of this B. So I'm going to multiply the top equation by 3 to make that happen. Let's get a little bit more room here. And so we will have, the top equation becomes 18 equals 3A plus 3B plus 3C, right? So I'm multiplying the 3 to each of these. The bottom equation we don't have to change, so I'm just going to copy it down. And now I will add these 2 equations together. Add the left-hand sides, add the right-hand sides. So we get 28 equals 12A. The b's cancel out, and then I get 4C. So that is my result from step 2. So let's see if I can get both of those results in the screen together. And so for step 3, I want to solve. I take the resulting equations from step 1 and 2 and solve them as a system of equations. So from step 1, I had 2 equals 2a plus 2c. From step 2, I have 28 equals 12a plus 4c. And I want to solve this as a system of equations of 2 variables. So I have to choose a variable to eliminate. I think that's going to be the easiest way to handle this. I'm going to choose to eliminate c, which means I need to make this a -4. So I'm going to multiply the top equation by -2. So I'll get -4 equal, everything will be -4. -4a minus 4c. The bottom equation I didn't have to change, so I'll just copy it down. And so we will have, when I add these two together, this will be 24. Add the right-hand sides together, I'll get 8a, and the c's get canceled out. And so now I can finally solve it for a and get my first result. I divide a on both sides, and I'm going to get a is equal to 3. Right. So the coefficient of x squared, which is a, has to equal 3. Right. Before I leave step 3, I don't want to take this value for a and plug it back into one of my original equations. Let's finish getting all the information out of step 3 that we can. We're going to take 3 for a and plug it back into one of these two equations to find c. So I can get a and c out of step 3. Then I will plug that back into my original equations to find b. So I'm going to plug it into the top equation because obviously the numbers are smaller. It looks like it'll be easier to manage. So I'll get 2 times 2a, which is 3. I said 2 times for some reason. 2 equals 2 times a, which is 3, plus 2c. And now I can solve that for c. Let's go ahead and separate that. And so I'll get 2 equals 6 plus 2c, subtract the 6 over, get -4 equals 2c, divide by 2, and you get c is equal to -2. Now I can find b by plugging these back into one of my original equations. You have 3 to choose from. Any of them should give you the same answer for b. So again, it's not a matter of choosing the right one to get the right result. They all give you the same result. It's a matter of choosing the one that's going to be easier to work with to make things as easy as possible on ourselves. So going back up to the original 3 equations, which are right here, a, b, and c. Sorry, I used the same letters that my variables were. It looks like equation A is going to be the easiest one. They're all positive. It looks just simple and straightforward. So I'm going to use this equation. 6 equals a plus b plus c to find my last result. Right. So that was step 3 right there. So step 4, we'll use this equation. 6 equals a plus b plus c. I'll plug 3 in for a, -2 in for c. And so I'll get 6 equals 3 plus b plus -2, which is going to give me 6 equals 1 plus b, right? So I'm going to combine these together. They're already on the same side of the equation, so I just combine them. 3 minus 2 gives me 1. That's how I got 1 here. Subtract the 1 from both sides, I get b is equal to 5. All right, and so that solves the system of equations, but the final answer in MathXL needs to be a quadratic function. So they want to know what quadratic function has the parabola that passes through those 3 points. The quadratic function is the function that looks like this. Sorry, I don't know why I did a straight line there. And so now we plug in a, b, and c to this formula. So y equals 3x squared, right? 3 was the coefficient of x squared, plus 5x, right? Because b is equal to 5, so we'll have 5 there, plus c, which is -2, so I'm going to put -2. So there's our quadratic function. This is the only parabola that can pass through those 3 points. There's only one parabola that can do that. And this is the equation for that parabola. All right, last problem. So I'm already at the hour mark. Again, I apologize. There is actually a pretty big shortcut for this problem, so I'll do it as quickly as I can. It is a word problem, however. Emma paid the $10.89 bill for her lunch with 248 coins. So probably not the nicest thing to do to the people working at that restaurant. Consisting of pennies, nickels, and dimes. If the number of nickels plus the number of dimes was equal to the number of pennies, then how many coins of each type did she use? So again, we have three unknown values. We have the number of pennies. Let's try that again. Number of pennies, the number of nickels, and the number of dimes. And I'll use letters to help me remember which one's which. So P for the number of pennies, N for the number of nickels, D for the number of dimes. If there are three variables, how many equations do we need to have a specific solution? We need to have three equations. And so one of the equations is very literal here. It's the next sentence. The number of nickels, that's N, plus, that's a plus sign, the number of dimes, that's D, equals the number of pennies, that's P. That's one equation that they just spell out for us. But the other two equations we'll have to do a little bit more digging to find. But they are based on the value of the coins and the number of coins that there are. Right? So there's 248 coins altogether. That tells me that the number of pennies plus the number of nickels plus the number of dimes has to be 248. Right? If I take the number of each of my coins and add them together, we're told that it's 248 coins altogether. For the $10.89, we have to be careful how we set up this last equation. It's not P plus N plus D equals $10.89. If that's how you set up the equation, I know it kind of makes sense because you're saying, well, if I take the pennies and the nickels and the dimes, that's $10.89 altogether. But these variables represent the number of the coins that we have. N is the number of nickels. It's not how much the nickels are worth. So if I have, 10 nickels, how much money is that, right? I want this to be the money that the nickels is worth. If I have 10 nickels, that's the number of nickels I have, but the value of those nickels would be 50 cents, right? 0.50. And the way I would get the value from the number of nickels that I have is to multiply the number of nickels by 0.05, right? Multiply how many nickels you have by the value of each nickel, and you'll get the value of your nickels, right? So it needs to be 0.05 N for the value of the nickels, 0.10 D for the value of the dimes, 0.01 P for the value of the pennies. And so there's my third equation. Now the shortcut here, which is very rarely available, and there's a couple ways you might see it, but the way I'm looking at it is this first equation that I have written here tells me that N plus D is equal to P. And I just so happen to have N plus D in my second equation. So I can use the first equation to swap it out. The first equation tells me that N plus D can be replaced by P. They're equal to each other. They're the same. And so N plus D here, I can take N plus D out and replace it with P. It's a rare case of being able to substitute two variables at once for one variable, right? So I'm replacing two variables with one variable. It doesn't happen very often. That's usually not an option, but this problem sets it up in such a way that it is an option, right? So N plus D can be replaced with P. I'm going to take this N plus D, replace it with P. The rest of the equation copies down, right? So we're going to have P gets copied down here. The 248 gets copied down here. So we end up with P plus P equals 248. We combine the P's together. So 2P is equal to 248. And we can solve it for P by dividing 2 on both sides. So we get P is equal to 124. So right away, that's a big shortcut, right? Right away, I find out there's 124 pennies. I still need to find the number of nickels and the number of dimes. So I still have two variables to deal with, which means I'm going to be basically solving a system of equations with two variables now instead of three. So it's still going to be a little bit of work. I'm going to plug this information back into these equations. Now, again, to save a little bit of time since this video has gone on for so long, if I plug it into this equation or this equation, I get the same information either way. So if I'm going to replace P here with 124, what this tells me is that N plus D equals 124. if I do the same thing here, if I plug in 124 here, I subtract the 124 to the other side, I get the same information. N plus D is 124. So the first two equations give me the same result. N plus D equals 124. I also want to plug in 124 here to the bottom equation. So what we'll have is 0.01, and I'll replace P with 124, plus 0.05N plus 0.10D equals $10.89. All right. And then I'm going to simplify this. So let's put this equation on pause for a minute, deal with this equation. If I have 124 pennies, what do I have? I have $1.24, right? So again, by multiplying it by 0.01, we get the value of those pennies, plus 0.05N plus 0.10D equals $10.89. I'll subtract the $1.24 to the other side. And so I end up with a better formatted equation of 0.05N plus 0.10D equals, when I subtract these, I'll get 5, 6, looks like 965. Hopefully I did that right. And so this will be my second equation. So I have N plus D equals 124, and I have 0.05N plus 0.10D equals $9.65. So we want to solve this system of equations of two variables. You can do elimination method. In fact, I bet Math Excel probably does it that way. And my recollection is that, they get rid of the decimal numbers here before they do that. I think it's just easier to use substitution method here. Now, substitution method generally doesn't work with system of equations of three variables. But since we're down to two variables here, I'm going to revisit that option. And I think it's an easier way to do this problem. So I'll solve the top equation for D. It doesn't matter which one you pick. I'm just going to solve for D. Subtract N to the other side. So we'll get D is equal to 124 minus N. And then I will substitute that into the bottom equation. So we get 0.05N plus 0.10. In place of D, we have 124 minus N equals $9.65. Distribute the 0.10 to the parentheses. So we get 0.05N plus, this will be 12.4 when I multiply these two numbers together, minus 0.10N equals 9.65. I'm going to need a little more room here to keep working. Combine the n's together, so it'll be negative 0.05, I forgot the 0, 0.05N minus 12.5, sorry, I don't know why I said 12.5, minus 12.4 to the other side. So I'm doing two things at once, combining my like terms and subtracting this number over to the right-hand side. And I didn't really leave myself a lot of room to do that. And so what do I get here? I'm trying to avoid using a calculator this whole video, and I haven't really felt like I needed to except now. So let me see if I can figure this out in my head real quick. It'd be 2.4, and then I think it's going to be negative 2.75. You might check me on that. If I'm wrong, make the adjustment yourself on your own notes. And then I'm going to divide by 0.05 on both sides. Negative 0.05 to solve for n. And I should get a nice answer here. It needs to be positive. It needs to be a whole number because otherwise it wouldn't make sense for this problem. So, and it looks like it should work out nice. Now, I'm thinking 20, 40, and then 15 would be 55. I think you should get 55 here. Now, the way I'm figuring that out is I'm thinking this is like a nickel, right? 0.05. And if I had $2.75 in nickels, it takes 20 nickels to make $1. So it takes 40 nickels to make $2, and then another 15 nickels to make 75 cents. So 55 is how I got that answer. Now I want to find the number of dimes, so I will do that by plugging it back in to this equation right here. I already have it solved for D, so I would take the result I just got in, which is 55, and then plug it back in right here. And I'll just do the work over here. Okay, I'm sorry, I just did that. Let's see if I can adjust it back. Okay. Sorry, I moved the recording screen. I hope that wasn't too disorienting for you. What I was trying to do, And what it kind of still did for me is kind of separate that off there. So, so here we have d is equal to 124 minus n. I'm plugging in 55 for n. And that's going to give me the number of dimes, which 45, 55, 65. I think we'll get 69. So the number of dimes would be 69. All right. And so that's the end of the problem. There's 124 pennies, 55 nickels, 69 dimes. All right. So that concludes the video on section 5.2. Sorry, it was a little lengthier than it probably should have been, but hopefully you found it entertaining and informative. And I will see you in the next video for section 5.3.